All right, we're back. We're back to designing this ping pong ball launcher shooter thing that we have started a week ago. So where we left off yesterday, we were already choosing our components for our design. We have chose our mechanism for shooting the ping pong ball, which is a tennis ball shooter mechanism, meaning we have two motors to rotate, and then we're going to launch the ping pong ball by sending it through a tube. So we control the speed of the motors, then we launch the ball. Pretty simple in theory until we get into practice and it becomes more of a headache. But yeah, so let's see. What can we do? Oh, we also went to the power supply and transmission. We chose our power supply, which is going to be a DC power supply. Again, the robot's going to be pretty stationary. It's going to have pan and tilt, but in terms of translation, it's not going to move. So DC power supply, that's what we're going to have. Power transmission, we're going to just use motors more than likely. Like, that's where all our power, majority of our power is going to. Raspberry Pi as well, to the camera. So there's that. We also chose our position control. There's not too much to choose because we're just going to buy this from, online. We're just going to buy it online and use it. So we're just going to do that. Besides that, let's move on to the next rating so we could start actually designing this thing, make it more interesting. So, yeah, we did, so we already chose, what was the last thing? I already forgot. We already chose our position control, so that was the third one, I believe. So what's the next one? Number 4, how to store the ping pong balls. Okay, so this is going to take into consideration of what shooting mechanism we chose, which is this one. That was the best mechanism we had based on our ratings. So, considering that, what is going to be our best ping pong ball system to move the ball? To be honest, I think it's just going to be the gravity fed one. The reason why the reason why I'm not saying, the reason why I think is the better option is because for the spring-loaded one, we have to put the ball in between the two motors, and that may be difficult because we kind of want the motors to have a tight tolerance so it launches the ball well. So let me try to draw out what I mean. So if these are the two motors, right? This is like a top view, and then this is our ping pong ball. We want the tolerance, like the gap between the ping pong ball and the motors, to be very small, so that they can grab onto the ping pong ball and launch them. So by that fact, it's kind of difficult to put the ball in between these two motors. So I think a better solution would be the gravity fed one, and that's because we could have it in such a way that the ball basically, again, this is still the top view. So if we had the gravity fed reservoir, or whatever you want to call it, if we had one of those, we could have the ball slide into the motors basically, and that gives you more of a nice flow than forcing the ball to go up in between the two motors, if that makes sense. So maybe if I draw it out like this, like that, the ball will just basically come out. We maybe have some sort of guide or rail, and then it would go into the two motors. So this is rotating, or actually rotating in that direction, and then the ball will just launch that way. Like, I think if you see what I mean, like the guide into the motors is easier to set up than to have a spring-loaded one where we have to force the ball in between the motors. I think I've killed that dead horse. Okay, so I'm gonna go with the gravity fed one. It's also simpler, I think. The only thing we have to do is control how many balls are going out at once. I haven't thought that far ahead. For the spring-loaded shooter, that already comes into play because we could basically have the height of the tube or whatever roof that goes above the ping pong ball be the exact height of the ping pong ball. So only one ping pong ball can go up at a time. So, but the gravity fed shooter does not have, or gravity fed reservoir doesn't have that. So that can be an issue. But regardless, I think that is still easier to control than the spring loaded clip or whatever we call it. So I'm gonna choose that one. Again, we could change it in the future, but as far as I can tell, I think that'll be our better option. So let's just choose that. And to be honest, our design is more than likely going to change from what we have originally, simply because we're going to see how it comes out, and we're going to start testing and stuff like that. So ping pong ball reservoir. I don't know how to spell reservoir. I think it's like this. That looks wrong, but I'm gonna keep it. So let's just draw what we had before. It'd be something like this. Maybe we want to put like a hinge or something so we could open up a lid, because again, orientation would matter. I mean, not orientation, but if we're gonna rotate the system, we don't want this to move. Or we could put it to the side of the platform so we don't have to have it move. I don't know. That's going a little too far. But maybe we could have some sort of lid. Or some latch mechanism. Something like this. And we put little ping pong balls inside. There we go. Okay. So this is the reservoir. Gravity fed. So that's what we're gonna probably stick with. The next thing we did, so let's cross that out. So the next thing we did is choose a live video feedback, or we started designing for live video feedback. So let's try doing that. I don't think there was much that we had to think about for that, besides where is it? Oh, right here. So yeah, we already basically said we're just going to use a Raspberry Pi and the Raspberry Pi camera and use the module that comes with it, and then code it in Python to figure out to do all the fancy stuff. So we'll just use that. So Raspberry Pi. Oh no, my bad. That's not what I wanted to put. This is the live video feedback, which is, was predetermined like a while ago, I think. 4. Okay. So live video feedback. So this is going to be a Raspberry Pi. I don't know how it looks. This usually looks something like this. Some pins. this. It's probably a port here. I don't know, something like that, and then these have pins. Like that. We'll call this Raspberry Pi, and then this is going to connect to some ribbon cable. Let me do this instead. So something. Something like this, or what I remember, and then ribbon cable, something like that. Yeah, so we're gonna use a Raspberry Pi and camera module, and then we're gonna somehow stream it to our stream. So there's that. Okay, so that's pretty self-explanatory. So our design is coming up. It's pretty much almost done, which is pretty cool. We got this far. So there's number 5. Number 6, control to the internet. Okay, this one's a tough one, because I'm going to say YouTube, because YouTube seems to be most active on the stream so far. I may change it in the future, but I'm going to say YouTube. So we're going to try to use their YouTube API. We can use Twitter. Nah. See, it's difficult, because I want Twitter, because it's kind of neutral between the two platforms. So people who are watching on Twitch or YouTube could just go to Twitter and then do its thing. But that requires them leaving the stream, which is what I don't want. But I also feel like I might get more traffic on Twitch than YouTube if I were to stream it. I don't know. But YouTube seems the most active right now. So I'm gonna say YouTube. I mean, the coding later is gonna be, or we can combine all the APIs so we could work with all of them, but right now, I'm going to say YouTube. We could change it later, as always, because the coding of the programming is going to be way later in this project, so we don't have to worry too much of it about now. What do I want to do? What's it called? Controlled over the internet. And then we draw this. We'll start off with YouTube, and then we'll probably add the other APIs if necessary. So YouTube API. The next thing we could do control to the internet. Okay, yeah, I lost my spot for a second. The next thing what we could do is sensors. Oh no, AI or to play against. Okay, let's go down here. Again, this is more up in the air because this is all the programming stuff. And I guess the mechanism as well. But we could add all this extra stuff. So we're going to use some sort of complicated well, not complicated. We're going to use a dumbed down AI version that feels like an AI version of something intelligent. So we'll think about that. But might incorporate a speaker. So all this stuff are like features or external items that doesn't really affect the design, the main design. So we could wait on this, I think. And then what's the last one? Sensors. I mean, it kind of depends on the AI or the computer or the PC that we're gonna play against. So those kind of go hand in hand, and I don't want to focus too much time on that because, again, it's not really the main aspect of what this project's trying to be. So I think we have what we got. I mean, I think we have everything that we might need to start designing, at least three-dimensionally. Hooking stuff up, that's a whole nother story. Wiring, stuff like that, that is another story. But we could start at least building this thing. Okay. So why not? Let's just start. I mean, we're gonna start researching a lot of things regarding the design, like what motors we're gonna choose, how big a ping pong ball is. Probably start doing a parts list as well, so we could keep updated on like what we need or what we should buy. So let's do that. I'm gonna do this so you guys can see my desktop. So let's open up Excel. Let's create a parts list. So let's say ID, description, let's do this, and then I don't know, price, shipping if available, price, shipping, what else? Link. We need the link. We also need quantity as well. Yeah, so we need quantity as well. Let's do this. Or actually, let's do this. Sorry. So that should look good. I'm just formatting these things so it's convenient later. So link, that's fine. Okay. Let's save this. This is parts list. Save this on my desktop. So we have this. So I mean, let's start off with the obvious thing. We need ping pong balls. So let's just put it here. So we need ping pong balls. I prefer Amazon. 50 pack? 12 pack? A 60 pack though? That's so many. I don't think we need 60. I need like 10 maybe. I want them in color so we could see them as well. Here we go. Yeah, something like this, I guess. I don't know. Or white. We go white. Regulation width, thickness, tournament weight. Okay. Let's yeah, let's do this. We'll use these, I guess. So oh, hey, what's up, Dane? No, it's cool. It's cool. You You're actually pretty early. Well, relatively early. You're not too late in the stream. Um, it's all good. Let me put this. So just to let you know, I've gone through the design. So I think this is our well, not final design, but like what we're gonna stick with. We're going to stick with the shooting mechanism. That's like the tennis ball shooter one. We're gonna use a power supply to power up our devices, and we're gonna use that pan tilt mechanism to rotate the thing. We're just probably gonna buy this. And then a ping pong reservoir, I think it'll be easier to use the gravity fed one. It'll fit the design of the tennis ball shooter. So there's that. Live video feedback, we're going to use some sort of Raspberry Pi. And a camera that is compatible with the Raspberry Pi. And then we're going to code it. And then we're going to control the internet using YouTube. I think YouTube might be the best bet. So that's how it's going to go so far. And besides that, I'm just going through like a parts list. I'm starting to like get stuff that we need to buy rather than build. So once we have that, then we can start doing some designing. So that's what I'm doing now. So ping pong. We need one, and the price. Let's see. $7.99, probably free shipping. So okay. I want the orange one so we could see it. So there's that. Let's make this bold. Okay. So there's that. Can I do? Let's not do that. Oh well. No, that's cool. I don't think you're that far behind, unless it's, I don't know. Maybe, I really don't know, but like maybe it's just the internet acting up. So what I was thinking for the ping pong balls. Oh well, let's start off with stuff we are gonna buy, right? So Raspberry Pi. We don't need to buy one, but we do need one. So I think it's model B plus. Need one of those. Price not available. I should put something like that. I think it fits now. All right, cool, awesome. Yeah, so I already have a Raspberry Pi, so we don't have to buy one of those. Or I could just put 0 here, huh? That would work. Yeah, it would work. Okay, so we don't need a link because I already have one. Okay, Raspberry Pi B. We need the camera module. So camera module Raspberry Pi. We need one of those. Don't have to buy it because I already have one. Need one of those. Okay. What else do we need? Ping pong balls we already got. We could technically look for one of these, but I don't want to look for one yet without having the mechanism at least designed a little bit, because the torque on the servo motors is dependent on how heavy the object is. So we don't need that. We need a DC power supply. Again, we don't need to buy it because I already have it. Power supply, DC, variable 100 NA, something like that. Why is it? Did I close it? I might have closed it. Okay, what else do we need? DC motors. So yeah, DC motors. Let's see. I'm looking like RC maybe. RC motors. Huh. Where would we buy those? See, I'm looking for probably one of these. Like, these are really cheap, but they're kind of low in torque, but that's fine because the ping pong ball is not heavy. So, does it tell us how much torque we get? See, we get 1600 RPM roughly, and that's actually quite a bit of RPM, but the torque is low. So, basically, I could like pinch the motor or the shaft of the motor, and it will stop. It's not really strong, you know what I mean? Even though it spins really fast. So, which is fine because the ping pong ball is not like heavy or hard to move. So I think one of these would be great. It's 3 volt. I prefer like a 12 volt one. These come with mounts. That's pretty nice. 24,000 RPM. See, these things are pretty gnarly. Huh. Let's see. DC motor. Uh, 3 to 12 volt. Here we go. This one also has wind turbine, hand crank, power generator, 1500 RPM. Yeah, we could probably use this one. It's just mounting it would be a pain. I preferably want one of these though. See, what's like its starting torque as well? See, I want one to be, I want this kind of motor, but like, with 12 volts or something. So we have more range to vary the speed, so we can control how far the ball can be thrown. That's why I want like a bigger voltage. See, this one's, we saw this one. Let me see, 12 volt. Huh. I don't know. I don't know which motor to choose, really. Besides, I want these, but I want a larger range of voltage. I don't know if maybe I'm asking for too much. See, these have 3 to 12 volts. But they look the same as the other ones. DC motors, 3 to 12 volts, no load, speed 9,000 RPM to 25,000 RPM. See, I want these motors. See, these are like, here, let me type in 3 to 12 volts. Maybe we'll find something that way. They're showing these. Three to 5 volts. Maybe? We also gotta mount it somehow. Here we go. This is better. We get 6 volts. So, power rating 0.25 watts, rated speed 5,000 RPM. That may be fine, actually. Testing voltage 3 volts. Okay. Alright, let's just stick with these, because I feel like this is our best bet. These are, yeah. Okay, let's try these. We get 2 of them, right? No, we get 5 of them. Okay, that's more than enough. Alright, let's just take these. It's fairly cheap, and they're like $1 each. So, we'll see that. I realize this is not one. Let's do this. A2 plus 1, like that. And then bring that down. Bring this down 1 more. Alright, motor, DC. What was it? It was 0 to 6 volts. Volt, 6 volt. And this is not the most exciting stuff, but you know, I mean, this is just, we need this parts list at one point. It's highly convenient just have it all in one place. So $7.99 free shipping. All right. It's like, I like how the ping pong balls are just as expensive as 5 motors. I think that's funny. Okay, so there's that. What else do we need? We need to mount these motors somehow. So we need some sort of DC motor mount. Pretty sure they have these. These could work, but it's not what I want. A bracket, maybe? Those are brackets, but it's not like... Do they have a better one, you know? Do they have a better bracket? RC DC motor. Oh, these came with... But how do you, like, attach it to something? Do you just glue it? I don't want to glue it. Huh. Maybe you... Oh, that's interesting. Maybe. Hey, what's up, Avichkin 8484? What's up, man? We're just going over through a parts list. If you're still here, I kind of missed your message, but if you're still here, yeah, we're going over a parts list. We just recently went through our whole design. It chose all our components. So we chose this for a tennis ball shooter mechanism, and then we also chose our power supply, position control, ping pong reservoir for storing the balls, live video feedback using a Raspberry Pi, and then we're gonna do some coding later for the YouTube API. Yeah, so there's that. Besides that, what were we doing? We were doing something. Yeah, we're looking for motor mounts. There have to be something there. DC motor bracket. It's called, like, I think it's called like a flat. Yeah, he might have left, to be honest. Oh well, it's cool. I don't want to. This is way too overkill. Like, I don't need that. Let's go to. Let's do this. Can I sign in? Hey, I still can't pronounce your name, man. I'm gonna call you OV for short. I don't know if that's the right term, but yeah. Glad you're here. DC motor. It's not this is the one. What is it called? There's a specific name for this motor. I'm just trying to figure out what it's called. It is brushed. What's up? What is this called? There's a motor for this. I just don't know the name. Common DC motor. This. What is it called? Well, these are pretty cheap. DC motor size. No, it's not called the stepper motor. Okay, it's this motor, but this motor has a specific name. Right here. This is what I was looking for. The 711 is a standard 130 size DC hobby motor. So if I search this, it's that, and then when we put bracket, it should pop up. It might be cheaper to buy them individually, but we gotta take into account shipping, so I don't wanna. Let's try this 130 size DC motor bracket. Yeah, these would work, but like, how would you mount it on something? Let's see. I remember seeing it before. I don't want to waste too much time on this, but because I want to start 3D modeling. I know I put it in the title. I don't want to be like clickbaity and not do any 3D modeling today, but I really want to start doing that. I just want to figure out this bracket, because I know I'll forget later on, and then I'm like, oh, what's that thing called? No, DC motor mount bracket. I remember seeing it. It's so simple. Yeah. Oh, here we go. This is okay. See, this is easy. You know what I mean? Like, all you have to do is clamp it down. The only problem is with this, depending on the accuracy of how the part is made, given this company or distributor, Tinkersphere, if they don't make it accurately, the motor could slip out. And this is later on in terms of design, but if you think about it, vibration is a thing when it comes to motors. So essentially, since the motor is vibrating over time, parts wear out. Meaning, since this is like some sort of sheet metal or something, it'll probably bend a little bit. So it might get a little loose and then probably fall out. But within our time frame, I don't think that'll be much of an issue. So this right here, I want 2 of these essentially. So we'll just take these. I remember seeing these. Okay. So we call this we'll call it a mount, motor, and then the size, I believe, what was it? It was 130. Oh, hold on. 130 size. Okay, we'll put size 130. Size 130, and we'll need 2 of those, and then we need the price, which is $2.99 plus shipping. It's probably very, very expensive for shipping because these are very light materials, so it's not really worth shipping the material in terms of a business perspective. But we'll need to figure this out later. So I'm gonna put a comment. Need to figure out. AM 06-09. Okay. Okay, what else do we need? I'm just going over this, our design. What else do we need? We need a ping pong ball. We already got those, YouTube API. We already have the Raspberry Pi, the camera. The position control we'll choose later after we design some stuff. Power supply we already have. We have this. We have the motors for the. We need the wheels, right? We need the wheels that go on the motor to actually get some grip on the ping pong ball and launch them. So that's pretty simple. if we go back to the motor that we chose, if we go back here, we have a 0 to 6 volt motor. Does it tell us? Oh, here we go. The size of the shaft is, if you guys could see that. Oh, I lost it. So, oh, it's right here. Size of the shaft is 2 by 8 millimeters, meaning, what, I mean, if you look at that, like, what does that mean? It's essentially the diameter by its length. So the diameter of the shaft is 2 millimeters, and the length of the shaft is 8 millimeters. So we need to find basically a car wheel, or toy car wheel, that has the inner diameter being 2 millimeters minimum. So we could probably browse around here and find one, but I guess not. Let me put 2 millimeter toy car wheel. We'll probably be able to find it. Yeah, so something like this. Size, I don't think size matters too much, because these wheels are very small and they're gonna weigh practically like nothing. But we could choose whichever one. We want rubber though. We don't want plastic. We want rubber simply because we want some nice grip onto the ping pong ball. Or at least I prefer rubber. And we don't want like wheels that look like this either. Oh, these are plastic though. Like we don't want not too much grip. You know what I mean? Like I think you see what I mean. See, these might be fine. The 1.95 millimeter hole is just slightly smaller than the hole, so we could just press it onto it and it'll work. Yeah, so let's try these. Why not? Yeah, so 2 millimeters, 26, blah blah blah. Ooh, if you see that, I don't know if you guys could see that. It's kind of thin. That kind of scares me. I don't know. It's probably not an issue, but it does scare me for some reason. Okay, if we have. Okay, I think I gotta worry about if we come back to the Photoshop just to draw what I'm thinking right now. So if this is the size of the, let's say this is a top view. If that's the size of the motor, the wheel has to be large enough to be just to be safe. We need the wheel to be larger than the motor's width, if that makes sense. So this is the wheel, and then the red circle is the motor. So we want it bigger. So the motor, so we say 26.2 millimeters. The motor is, does it give us 0.78 inches, which is great because it's not the right unit. So 22 or 26.2. I believe that's, so it's an inch. Okay, so it is, if I go back, so it's roughly a 1/4 inch bigger, or an 1/8 of an inch bigger relative to like the outer circumference, if you guys follow me there. Yeah. So an 1/8 of an inch is like pretty much like that big. So that's that much bigger than the motor. I feel like that's too much. That's too tight of a tolerance. We should probably go bigger. So if this is 26.2, we probably want maybe a 1/4 inch, or yeah, roughly a quarter. So maybe double the size. So do we have anything that's like 40 millimeters? Here we go, something like this. So 10 pieces, tires 16 millimeter. No, we don't. I said 40. Huh, okay, let's go back. 30 millimeters is better, but we want like something a little bit bigger, I think. It also gives us more torque onto the ball, meaning more force, which can be a good or bad thing if you want to think about it a little bit more. But okay, I think it's kind of hard to choose one now. How about these? These may be like, these are really nice. See, the diameter is 65 millimeters. How big is that? So 65, 2.5 inches. That's like that big. Will that be too big? Maybe. How about the width of the wheel though? How big is that? Does it tell us? It doesn't. 2.5 inches. That's it's like my thumb, like the width of my thumb, something like that. That may be big enough. Hold on. Let me try to get a caliper real quick. Hold on. Okay, so let me close that. Okay, so 2.5 inches. Oh wait, that's way bigger than I thought. Okay, so 2.5 inches is roughly. That doesn't seem right, but I guess it is. Yeah, so it's this big. It's like, relative to my face, it's like half my face. I think that's a little too big, actually. I'm looking more of like maybe 1.5 inches, something like that, or 1.25 inches. And what that is in millimeters is roughly 30 millimeters. So let's go in that ball range or ballpark of size for wheels, because it's probably a better start. Do we have anything like that? Maybe I should go to shopping. Here we go. We get 10 pieces, more than enough. The width though, I'm scared about like how wide the tire is. It might be fine, to be honest. Maybe it is fine. Is the inside diameter? Oh, here we go. The height is 10.5 millimeters. What does that mean? Okay, so that must be the width of the tire wheel. So 10.5. So it's roughly that big. It's like, I don't know, like my pupil. Well, relative, I guess, like the closer I get, the bigger it gets. But I realize this is not a good scale for you guys. But it's roughly 1/2 inch. Okay, yeah, I think that may be fine. I think this will be fine. Again, for now, we don't have to stick with everything we have. We could change later, but it's really a good starting point. So let's put that down. Well, before we use this one, let's just check. What's the diameter? I believe it's 2. Again, like 2 by 30. Yeah, I think we're fine. Okay, yeah, let's just use these. That's fine. Wheel, rubber, 2 millimeter shaft. What is it? 30 millimeter. OD. Okay. We'll need one of those, right? Because it gives us 10. gives us 10 pieces. So how much was that? $280 per lot. We don't know the shipping yet, so we'll put a note there. Comment. Need to figure out. Yes. Put my. Okay, and then that. Oh, it's from AliExpress. That's gonna take forever to cut here. 30 to 50 days. You gotta be kidding me. Oh no, 30 or 50 days. That's so long. That's such a wide. It's like plus or minus a month when you might receive it. Like that's pretty bad. Alright, well, we'll keep those there for now. Maybe we could find another one from a different place. Like, how about this one? These might work. Maybe we could use some of these 40 pieces. That's so many. Yeah, maybe we could use one of these. 5-spoke rubber tires for a torque set of 20. You get like double the amount. Maybe we'll put these here instead for now. Or you make something cool like this. Okay, we'll use these instead because I don't want to risk the long wait. It's not worth it in my opinion. How much was it? We get 20. Was it this one? I think it was this one. Or no, it was these. 323. Well, it's slightly more expensive, but at least we'll have. Wait, I didn't even check the shipping. I just ignored that completely. Friday, June 26th. We're in June, right? Yes. Okay. No, that's fine. I don't. That's better than 2 months. So 323. Okay. And then what else? What else might we need? PVC pipe. That's what I really wanted to figure out, because the problem with PVC pipe, or any pipes in general, is that they have standard sizes. So if we don't know the size, well, let's start off with the size of the ping pong ball. Then we could start determining the size of the tube or the PVC pipe. So if we click this, let's close all this stuff out. What does it say? 40 millimeters. So, I believe that's like an inch and a half. Inch and a half. Ooh. Damn it. Okay, the problem here is that an inch and a half is the standard size for pipes, but the next standard size, I believe, is 2 inches, which is an issue. Well, let's check. Standard pipe sizes. Here we go. Usually, or better yet, what we could do, go to McMaster or Home Depot, really any hardware store, they should give us PVC sizes. So we want, standard PVC, I guess. And here, can I can't zoom in. Maybe a little too big. Okay. Can you guys see that? I think you guys could see that, hopefully. But the standard sizes are these, which I believe is the inside diameter. So it goes 1.5 to 2 inches. The reason why that can be an issue is because the ping pong ball will have the ability to like bounce inside the tube, which is what we don't want. So like, let me draw it out. Maybe it makes more sense if I draw it out. So like, let's say, this is the tube wall. Like this is the top view, and this is 2 inches wide. Right, 2 inches, and then we have our ping pong ball, which is 1.5 inches. So it looks something like this. So that means if we were to launch the ball, it has the potential to like rattle off these walls, not giving a very clean shot, and a lot of its speed can be diminished if we hit these walls. So we want the pipe to be as close to the ball as possible without like having the possibility of the ball getting stuck in the tube, if that makes sense. So we can make that a custom part. It might make more sense to make it as a custom part simply because we have to incorporate the motors and the toy car wheels within the design. So we'll have to like cut into the PVC pipe or do something about it before we could even use the pipe. So that could definitely be an issue. Okay, well, um, I'm gonna leave it as that right there. I'm gonna be right back. I'm gonna go use the restroom real quick. Hopefully you guys will stick along, but I'm gonna go use the restroom real quick. I'll be right back. Okay, sorry about that. I just had to go use the restroom. Okay, so back to what I was saying. We need a PVC pipe. My hat's a little messed up. Uh, we need a PVC pipe or some sort of pipe that needs to be as close as to this well, let's calm down. We need the inside diameter of the pipe to be as close as possible to the ping pong ball so that we don't have the ball rattling inside, which can lose energy or speed so that the ball won't actually get launched. And it brings in more of an uncontrollable factor within the design, so we probably want to eliminate that as much as possible. So with that being said, I think we could probably just 3D print the tube to meet our specs, because that gives us the benefit of how we want to mount the motors and control the width of the tube. So I think it makes sense to actually make that a custom part so we don't have to buy. So that may be a lead into some 3D modeling. But before we start jumping into that, like, what else can we potentially buy? Well, I need some sort of wire. I have wire, actually. I have a spool of wire. I have soldering. I have a solder. Have soldering iron and a soldering iron. So there's that. For the gravity-fed reservoir, we could potentially just buy some sort of plastic casing, or I could just get like I was gonna say a liter of soda, like the plastic bottle. Maybe we could use that to store the ping pong balls. But the problem with that is that the nozzle is not large enough, so we have to attach our own nozzle. So there's that. We'll need a lid somehow. We can also 3D print this. Like, it's unnecessary. It's highly unnecessary to 3D print it because it's just a container. But we could add a lid to it. So yeah, I think with that being said, I think we can start 3D modeling. So hopefully we can do that. So these are all the items that we have so far. Looks like it's roughly what, $20 for the parts we need, at least so far. That's actually not bad. The rest of stuff I have. So with that being said, I think we could start 3D modeling. So this may be even more boring than before. Some people might be really into it. If you guys have any questions about 3D modeling, let me know. I probably can answer most of them, but what I'll be using today is going to be SolidWorks. If you guys are familiar with SolidWorks, if not, it's powerful. It's a powerful 3D modeling software. Oh, that's I don't want to guys show you that. That's actually a sneak peek to my next video, but you guys didn't catch it, hopefully. The next video that's gonna come out on my YouTube channel, I think, is gonna be great, or it might be like the worst thing I ever made. But I don't think. I think it's gonna be really fun to make. Hopefully that'll come out next week. Probably not. Probably by the end of this month for sure. But I have a lot going on. I have high potential for, or a high standard for that one. But anyway, so let's go to our overlay so you guys can see. No, I guess I'll show you guys the application a little bit. So for those who are not familiar with SolidWorks, I'll just show you what you can do. Okay. We'll just start off designing. So we know from our ping pong ball. Let me pull this up again. Hopefully it pulls. Oh, okay, right here. It's 40 millimeters. What is 40 millimeters? 2 inches again. 1.5748. That's probably way more accurate than I need to be. But let's design a ping pong ball. We're gonna use this in our 3D model anyways, so it's good to have a reference point. So what you can do in a SolidWorks file or a part file is create a SolidWorks part. It's kind of self-explanatory. So how you build a part is essentially you imagine your part in a that's three-dimensional, originally did 3 dimensions, and then you uh, translate that into a 2-dimensional object. So a good way to put that in perspective, maybe it's easier to show you, but let me try to give you an example. Like if you look at a sphere, this like head on, if it were just like a painting or just a still image, that sphere would look like a circle, right? So from that, you could kind of understand that the sphere at you can understand the sphere in a 2-dimensional way, if that makes sense. Maybe I'm confusing you guys, but like here, so basically you go to a plane, you click sketch, and you sketch what you want to draw. So let's say we want to draw a circle, and then we could also determine the size of the circle, which was this. So that's 1.5748 inches. I have my settings set up in inches because that's what I usually work with. Metric is the superpower, the super race, but I work with inches like day to day, so I'm more comfortable with inches, to be honest. But I don't mind metric, like unless I'm in school, I prefer metric because it just makes everything highly convenient, like solving problems and stuff like that. So what I did here, I cut the circle in half, simply because the next step of what I'm gonna do is basically take this shape, this 2-dimensional shape, and rotate it around this vertical axis. So if you imagine that, you could rotate this half circle, and if you rotate a whole 360 degrees, you'll get a sphere. So if I were to go to like a isometric view, that's what this view is called, the 3-dimensional view, so to speak. It'll show the half circle in the plane. And then essentially, I could go to features in this top left corner and put revolved base. And basically this is what it does. You choose your axis of revolution, or the axis of rotation. You choose that, and then it already has my sketch selected. It chose the shaded part, the half circle, and then it revolved it around that axis. And then what I do, I'll just go like that, and there we go. We have a ball. Well, actually, I did this wrong. So this is a little. Well, let me do this first. So let's make this the color of the ball. So I don't know. It's like an orange, right? Let me go to advanced. Make this a little brighter. Ooh, that's like the color, right? Let me see. I don't know. I like 3D modeling and making it like highly detailed and like exact to the real thing because I don't know, it looks cool. Let me see. So if we go back here, right, it's roughly the same color. I mean, it's kind of hard to tell, but I think that's close enough. Okay, so let's give it the color. And the problem here, the issue what I was talking about earlier, the issue that I did is that the ping pong ball is not a solid. I mean, it is a solid, but it's not fully all material. It's hollow inside. That's what I'm trying to get at. So although I messed up, I could still edit this feature. So like what I could do is go back to the sketch, you know, edit it, and then make it a thin feature. Yeah. Or what I could do here is basically recreate a circle. Hopefully you guys get the concept of this, but recreate the circle, and then I could define the thinness of the wall of the ping pong ball. I don't know. This is more guesstimating than anything. 0.01 is probably a little too small. 0.05. I feel like that's small. I like using calipers to give me a sense of perspective, because sometimes numbers are just weird when you look at them. I guess it's still too big. I say half of that. 0.025 is probably a better number. So So there's that. And then you could also edit the sketch. So I'm gonna trim that so that basically I have a shell or a thin wall around the circumference of the ping pong ball. And then what I could do is exit the sketch. There's a problem with the sketch, and that's because I created that sketch, or, oh no. Here, let me do this. So we're gonna convert this to construction, and then close this off, so we get a nice shape. So if I do that, that should fix it. Okay, there we go. Now you're like, who's gonna notice that? No one is. No one's gonna give a crap about that small detail, but I at least know it's there. But to prove that it is there, we could also change the view to see-through. So basically, we know it's hollow. It's this little, you see this little dashed line that shows the inside wall of the ping pong ball. So there it is. So there's that. You go back to basically a non-outlined ball or an outlined one. So there's that. That's the ping pong ball. Probably the easiest thing we'll make this when it comes to 3D modeling. Possibly the easiest thing, besides downloading models and using them. But that is probably the easiest. So I'm gonna save that. Don't look at this. This is a teaser. Don't look at it. I should probably do this off screen so you guys don't see any spoilers. It's not really spoilers. I just want to keep it a surprise. But let's see. I'm missing. Where do I put this? YouTube projects. That's not the one. Sorry. I'm just trying to organize it so I could find it later. Let me do this. SolidWorks. We're gonna give this 005 dash 01. So we'll save that. That's the ping pong ball. Okay, so that's a simple model. I also, if you guys are curious, just in case I'm gonna put this online somewhere, I'm probably gonna explain it anyway. But I'm naming it in terms of my projects that I recently have, for at least this YouTube thing or Twitch in general or streaming. Project number, then within that project number, if I have a SolidWorks file, I'll just increment the number by 1. So this is the first part in my own project. And project 5, if that makes sense. So that's how the numbering system works. Not that it matters too much, but okay. What else we're gonna do? What else do we need? I think the next step is design this thing, the tube. So maybe I could show you an assembly how that would work, but after we design the tube, at least a little bit of it. So we're gonna create another part. I guess you guys could kind of guess how I'm going to make the tube. Pretty straightforward. I'm going to go to the right plane, and I'm going to draw on it, and then I'm going to make this the inside diameter. So again, we want the ping pong ball, or the tube, to be almost, or slightly bigger than the ping pong ball. 1.5 inches, I would say 1.625, an eighth of an inch bigger. Or actually 1.75. I think a quarter of an inch bigger is probably better. So, what did I say? 0.75. No, 0.5. Wait, what? No. Okay, wait. If the ping pong ball is 1.5 inches, I want it 1.75. So a quarter of an inch bigger. So, like roughly this much space. Again, the perspective is not that good, but quarter of an inch. So the reason why we can't buy the PVC pipe, for those who weren't there, we can't buy the pipe at a standard size that is 1.75. It goes 1.5 inches, then 2 inches, and I believe 2 inches is too wide for the ping pong ball, which would cause it to rattle when we launch it. So 1.75. So we'll do that. And then the thickness of the pipe, I don't know, 1/8 of an inch, which is 0.125 inches. So like roughly that thick. I guess that's too thick. That's fine. We go 1/16 of an inch. Yeah, let's go 1/8. We'll stick to 1/8. So what I'm gonna do is offset entities, do that, and then make this 0.125, which is 1/8. And then we have our shape. So this is going to be our tube. If we go like this, we could extrude it. We're going to do mid-plane. And then how long do we want it? I don't know. The shorter the better, I think. There might be a reason why gun barrels are long. I'm pretty sure that increases the accuracy of the bullet. But I also think the bullet is also dependent on the spiral of the bullet, because I believe when the bullet is shot, if I don't know too much about guns to be honest, but when the bullet is shot, at least in a rifle or a long range rifle or something, I think the bullet inside the barrel actually spins to stabilize the orientation of the bullet. It's like throwing a football. If you threw a football and you just threw it like a chest pass, like in basketball, it'll start doing this thing, it'll just go all over the place. But if you spiral it, it'll stay along its axis of rotation, because it's a very stable state for the ball, if that makes sense. So I don't know, maybe it's not related, but I think if we decrease the length of the tube for the ping pong ball, I think that would be better, because it reduces the risk of it just moving inside the tube, potentially causing it to slow down, which is what we don't want. So, I'm thinking maybe like what, half foot? Is that too short or too long? That's half a foot. It's like less on my face. I don't know. Maybe 4 inches. Yeah, let's go 4 inches. We'll stick with that. So 4 inches. We'll do that. We'll launch it. Okay. We'll do that. Tube. So there's our tube. So I guess this is, let's show another thing. We don't have to really do this now, but what we can do is create an assembly. So what I've shown you so far are just part files, meaning it's a singular part. I don't know how to explain it better than that, really. But there's also assemblies, which is the accumulation of parts that work together to do something else. You could think of it. I think it's self-explanatory, but you can think of it as like this caliper. One part would be like this head over here, like this metal piece that moves up and down the slide. That'll be one part, and then the other piece that stays stationary relative to my hand, or the one that's moving now, that's the other part. And then you put them together, you get an assembly. Obviously, based off that definition, assemblies can get very complex the more parts you have, or even the complicated design or geometry of the assembly. So let me show you what an assembly is in SolidWorks. It's pretty self-explanatory. We'll say we'll make it an assembly from the part. So we'll make an assembly. So now we could just insert our part, which is this. So now it's an assembly. which means we could add more parts. More parts to the assembly. So what we could do is insert components. We're gonna browse, go to the ping pong ball, and now we could place it in our 3D space. Now the problem, the most common thing you do in assemblies is to define the part relative to the other parts, or at least the base part. The base part is this tube, and knowing that the ball ideally would just go within the middle of the tube. So what we can do is create this thing called a mate. It's basically a relationship between it. It gives a relationship to between other parts, or at least relative to other defined geometries such as planes, lines, points, and so forth. So we're gonna mate this within the inside diameter of the tube. We're gonna make it concentric. That's a geometric relation, meaning concentricity, meaning the center point of two circles line up regardless of the size of the two circles. And I think it's easier to show that than explain it. So I made the ball concentric. So if I click on this and go normal to this assembly, if I go normal, you can see that the ball and the tube are concentric, meaning that they share the same center point in terms of the diameter of the parts. So they share the same diameter. And then the cool thing is, since we didn't restrain the ball, we could just slide the ball in and out of the tube. So you do something like that. So boom. Since we're here, let's just check if this is an appropriate size for the ping pong ball. For the tube. I think it is. Obviously, this virtual thing doesn't mean anything. Like, if I zoom out, yeah, it looks fine. You know what I mean? There's no scale represented to it. But, I don't think there'll be interference. I think this is tight enough where the ping pong ball won't be an issue when it'll just rattle against the wall or something, or lose speed. And I think the length is pretty decent. It's not too long. So this could work. Obviously, if we're going to make this a custom part, the dimensions of the part, of the tube at least, is highly dependent on the accuracy of the 3D printer. I'm more than likely going to make a 3D print. So essentially, so the tight tolerance of this, I believe, was 1/8 of an inch on each side, is only going to be as accurate as your 3D printer. Since there's one at work, and the company has a pretty decent 3D printer, like it's like 3K or something. It might sound like a lot of money, but in terms of like a company's perspective, that is like negligible, even for a small company. But it's more than good enough to meet this resolution. I believe the resolution of the 3D printer at work. Let me look that up, actually. I know what kind of printer it is. It's called the MakerBot Replicator. Replicator Plus, I believe. Oh, it's like 2K. Yeah, I think it's this one. But its accuracy, I believe, is 0.5 millimeters, which is pretty damn good. Let me see if I can pull that up. So I'm just gonna probably just use the one at work. Don't tell my boss. Oh wow, here we go. 100. Well, that's layer resolution. Well, I guess that's the same thing. 0.1 microns. That doesn't make sense. Not 0.1. Okay. Well, let's see what 0.1. How accurate is that? Well, that's a 0.003 of an inch, which is pretty damn accurate. So even though this looks very tight in terms of tolerance, the 3D printer I'm working with will pretty much make this on point. Now we're out of control when it comes to the ping pong balls, the accuracy of the width of them. So the width of this ping pong ball could vary from like an inch and a half to, I don't know, maybe inch and 5/8. Inch and 5/8 is roughly 1.625, I believe. So if we measure that, 1.75. Yeah, so I think we'll be fine. We might need to make it a little bigger. I don't know. I mean, it's really up to us, but we'll leave it like that for now. So that's an assembly. That's essentially the assembly. We won't need to save that for now. But coming back to this. Kind of need the motors to design it. We also want the reservoir somehow connect to this thing. See, what I'm thinking is like we cut some slots here. Or maybe not. Like what I'm thinking, maybe cut some slots here, put the motors here so that when the ball goes through this tube, it gets launched out. We could potentially do that. So let's just see how this looks. So I'm gonna do my sketch again. I don't know. Maybe 3/4 of the way up. Let's see. The outside diameter is 1.875. Jesus, wait. What's 7/8? How much is that? 0.875. Okay, so if I go down 1/4, that's roughly, oh, my head hurts. 625? Yes, 625. Damn it. No, that's not it. 6. That doesn't make sense. Oh, because it's an inch. Okay, wait, hold on. Maybe that seems too high. Let's go an inch. That's better, I guess. We need the width of it to roughly be the size of the wheel, which was 40 millimeters, I believe, or roughly 40 millimeters. Inch and a half. Oh no, it wasn't 40, huh? Hold on. Where's this one? Outside diameter. That's what we needed to be the minimum size of. 30 millimeter. 1.18. So it needs to be roughly 1.25 inches. So let's do this. And then we'll probably, I don't know, put this somewhere like, what, 0.5? You'll see what I'm doing in a bit. Let me see. Ooh. No, I think we're fine. Never mind. I guess we're not. It's kind of hard to design it without the motor. Maybe we should look up the motor, see if we could find it somewhere. But let's see. They're all both. So now we have a slot. Well, that doesn't make sense, right? We need the bottom pipe to be there, because like without it the ball will just fall down, right? Unless we rotate it. We could rotate it this way, like this is the bottom side and this is the top side. But that doesn't, I don't think that works really. What we should do instead of that, not this, hold on. If we go normal, let me sketch. Let's get rid of this. Delete. Maybe what we should do is something like this. So we define it relative to this edge. Maybe this is 0.125. Maybe a little bigger. 0.25. 0.75. A lot of guesstimating comes to this. That's not right. Let's do 0.625. 0.5. That might be good enough. Okay, we said this needs to be at least 1.75. Is that what we had? 1.185. So inch and a quarter. My bad. Let's do inch and a quarter. And then make this 0.5. And then the height of this is going to be like the height of the wheel. Which I believe it doesn't tell us. I'm going to say roughly 10 millimeters. So what is that in inches though? Did that work? I can't tell. Oh, it did work. Half an inch. We'll just say half an inch. So this, let me accept that, and then exit our sketch, and we have a slot that goes through. So hopefully, this is enough room for the wheel, and then we can put the two wheels on this side, and then launch the ping pong ball. I realized we should have it in the center. I don't know why it wasn't obvious before, but we should have the slots in the center because that's the center of the ball, right? So if we look at this is the center of the ball is gonna be concentric, or roughly concentric with this cylinder or this tube. So we should actually just make this centered, essentially. So what we can do is change this, get rid of this. Oh no, keep that. Get rid of this one. So now we could still move this up and down. So we could create a geometric relation, making it horizontal, so we could do that. So there's these things called geometric relations. I don't know if you guys are familiar with these or even worked in SolidWorks. This might be new for all of you, but how it works, we can create different kinds of dimensions or defining points to define our shape. The things that we need to define to be our shape to be fully defined in this sketch. Okay, wait. Yeah. So like, let's say if I didn't have that dimension, there will be blue lines, meaning it's still able to move. This whole sketch is still able to move, which is a good or a bad thing depending on how you design in SolidWorks, but I prefer everything to be fully defined. Since this is still able to move, it's not fully defined. So what I have to do is define this position, and then it should be fully defined. But you don't have to define it relative to some other basis or some sort of wall or reference point. We could define it in terms of geometry. So like what I did before is like I chose the center point on this line, and I want it to be horizontal with the origin, so that way that the rectangle is always in the center regardless of how I update the size. So I'll show you that right now actually. So if I exit the sketch, you see that the rectangles are in the center, or the center of this circle or tube, and that will always be true regardless if I update the size. So let me go over here and let me update the size. So if I go here and update the sketch, so let's say I want to make this bigger. I'll make this, I don't know, 5 inches. And then I'll update the whole thing, and what you'll notice is that square or rectangle is still in the center because it's defined geometrically. It's not based on a relation or a physical dimension, so it'll stay in the center. So that's what I did there. So let's change this back. Go like that. So there's that. So something like that. And then we put the ping pong ball in the middle. Okay. Let's before we move on, let's start getting some parts from online, because I'm not going to be able to 3D model everything. And it's just more time efficient to look online. So there's this actual community called the GrabCAD. If any of you guys are familiar with it, but there's this thing called GrabCAD. Basically, it's a website that other engineers or 3D modeling hobbyists basically upload their work, and then they're free to download. Sometimes they don't have the file types that you want, but usually they do. They usually have something that you could at least work with. So if we go to the community, we could search, like, see, someone 3D modeled this, which is pretty insane. They probably use, yeah, I don't know, never mind. I don't know what they used, but they 3D modeled this, and it's pretty crazy. Like, I don't know. Do you guys want to see this? I don't know if you guys want to see this, like, in a 3D, in the actual thing. Hopefully I could sign in. Hopefully no one spams me. I realize this is sensitive information, and I could just do this, and you guys won't be able to see it. But I guess it doesn't matter now. Download. So let's try opening this up. Maybe you guys will be interested in this, because I think it's very cool. Like, someone was able to design this. That's insane. I don't have the ability to do that yet, or at least I'm hopeful. But let's see how this looks. Yeah, so there's other crazy stuff here. Like, people designed this. This is probably fully operational, or at least can be simulated. These are a lot of manufacturing things. This is like a 3D printer. Someone modeled that. This is a legit 3D printer. What else did people make? Like, someone did like a brake caliper. Oh no. Or a disc, or a brake drum. These usually go on the rear end of vehicles. But yeah, look at it. It's pretty crazy. It's highly detailed. And people like designing or building it in SolidWorks or any kind of 3D modeling system is like step 1. Step 2 is like rendering this so it looks good. Like, that's a whole nother thing. Like, this is a nice render, and look at the color and the lighting and stuff like that. That's a whole different scenario, which I have not dealt with yet, which I would like to, because it makes stuff look really nice. Like, someone did this. Like, that's pretty crazy. They did an aircraft. So let me show you that Jaguar. Hold on, it's loading, sorry. Let me extract it, and then we'll get to look at it. Extract, yes. What do we have here? Oh, wow. They made it in SolidWorks. And I might be able to open it. Hold on. Oh, it's a step file. Okay. So there's different type of files for 3D modeling. There's a common one known as a step file. Essentially, a step file is not dependent on what version of SolidWorks you're using or what kind of software you're using. Typically, most softwares can work with step files, and essentially what the step file does, it's just readable, more compatible with different software. So you can open this up with anything practically, or anything with quotation marks. But yeah. So right now it's trying to build it. This might actually take a bit. We'll just leave that in the background. Oh, I guess I can't. Okay, well, we'll just look at more cool stuff, I guess. But essentially, the step file just rebuilds the part. Rebuilds the part within your software of your choosing. So I guess we have it here. I mean, this is pretty cool. It shows black, but yeah, looks pretty nice. Like, we could do, maybe you could see it like this. Like, this is highly detailed. This is like what I like doing, just making highly detailed, like, 3D models. Like, look at this thing. Like it's pretty crazy. Is there anything? Okay, this looks like just like a toy car. Maybe that's what it's used for. But yeah, look at that. It's pretty cool. So yeah, you do some crazy stuff with this software. But yeah, there's that. I mean, nothing too. Let's see if there's anything inside. No. So looks like he just did the most important parts, really. But yeah. Like, the cool thing about this, you could like, which a project of mine that I want to do in the future is, if you have like some sort of car, or at least the parts of a car, a 3D model to an extent, you could import that into a game called Assetto Corsa. It's a simulator, a racing simulator that you could race in. Pretty self-explanatory, but you could input the car model in that, and then map the different components of the car to the game's program, or it's not a program. What's that word that people use in coding? It's a class. So you basically map your part file or 3D model to the class attributes or properties, and then from there the game will read it as any other car, and you can actually drive this car and have fun with it. You also could change like the physics of it, and like the sounds of it, what sounds it makes. So like that got me thinking, like I wanna do that one day. I don't know when, but hopefully maybe we'll start on that sometime this year, maybe the next year. I don't know, because that's definitely another big project. But yeah, so you could import that into like a video game. So I don't know. I thought that would be cool. We don't need that anymore, by the way. So let's go back to what we were doing. What is it? Okay, it's 8:15. So we have another 15 minutes. For those who are maybe new here, I don't know. Hopefully my stream did it come. Oh wait, hold on. Sorry, I just got sidetracked a little bit. I just want to check something. I don't want this to mess up. Oh, I'm sorry, Sigma Pi. If you're still here, I'm sorry. I didn't see your message because my chat was off. It logged out. I just noticed that. So, yes, difficult stage in design is assuming the dimensions. It is, because like when you actually build it, there might be tolerance issues and stuff like that. Yeah, I know. They made this crazy thing like a while ago. So, yeah, sorry I didn't see your chat or your comment earlier. I didn't know my chat went out. Sorry about that, guys. But it should be good now. I'm just gonna stay on the YouTube website and keep it there, because that seems like that will stay working. Okay. So what we want to do is do a DC motor. Search for a DC motor. I think it's 130 size. DC motor. So like this one. This is like the one we're gonna use. Do we have? So we don't need all this extra stuff. Like, we're not gonna see this. There's no point of that. I just want it for size or for fitment. We don't need it for all these other details. But I guess we'll just get these. So let me get that going. Extract. Copy. Sorry, I'm just trying to make sure my files are organized so I don't have a headache later finding these things. let's open this one. Oh, there it is. So there's our DC motor. It's pretty nice. It's pretty highly detailed, which is kind of unnecessary, but it looks cool nonetheless. So we'll save this. Yeah, okay, we're fine. So positive, negative, I don't think, when it comes to DC motors, positive, negative doesn't actually matter per se. The only time it matters is that you got to get the polarity right. So if you plug in positive here and then negative on this side, it'll cause it to rotate in one direction. But if you swap the wires, the power and ground inputs or outputs, however you look at it, if you swap the wire, the motor will spin in the opposite direction. It basically reverses the polarity of the motor. So when hooking up, we got to make sure we have the right side or the right orientation for the wheel to spin, because we want it to spin going towards outside the tube or towards or in the direction that the ball is going to be launched, right? So it makes sense. We probably might rewire this or wire this incorrectly at first, because I've done that hundreds of times. Not hundreds, maybe like 10 times, but not a motor specifically, just soldering in general. Like I'll just like, oh, I know how to build it, but then I don't have a schematic, so then I'll mess up and have to desolder, resolder, and it's a whole mess. But yeah. So what is that? Now I'm worried. Let's make an assembly again. Maybe I should just keep this assembly. So make assembly. Put that there. Insert components. No. Sorry, I don't need this. Insert components. We'll put the ping pong ball. Insert the motor. Oh, I need to save that. Hold on. Oh, I didn't even open it. Let's do this. Concentric. There's that, and then we'll put the motor. If I could do this correctly. Can I open this? Okay, I want to save this as a part file. So I'll save this. Oh, I think that's what was messing me up. Okay, I think we're good then. Okay, now we could insert the part. That's not the one. This is the one. Put that in. And we need 2 of these, one on each side, like that. And then we'll orient this relative to the planes. So we'll choose this. Let me see. It'll be like that. Not coincident, but parallel. And then we'll keep that there. And then I don't know what direction we need it to be. As of now, we'll just keep it as generic as possible. So we'll do that, and then we'll flip the side, and then we just want it parallel. So we'll do that. So now we could just, it still can rotate. So what we'll do, we'll make this also horizontal. So we'll make these 2 parallel, and then we want the top of this to be parallel to the top plane. That way, this is always vertically up. Something like that, right? So we want to put the sorry, I just want to make sure my chat's working. I don't want to miss anything. Okay. So it's starting to look how we designed it, like all the way back over here. It's starting to look like what we did a long time ago. Not a long time ago, the past week or so. Like we already put in 8 hours into this, so we should be relatively far already. But you know, designs might change and all this crazy stuff might happen on the way. But we're pretty close, I think. Okay. So all we need is the wheels. So if we put the wheels on the shaft, and then we'll be able to launch the ping pong ball by having the wheels rotate, and therefore it should do what we need it to do. One thing is, like, how are we gonna have how are we gonna mount the motors? That's what I'm trying to think about right now. Because I already looked up that we're gonna use a, how do you say it? What does it look like? Where am I at? This motor mount. So essentially, what we had before, we're gonna use one of these brackets. It's aluminum, or probably aluminum. It's not a sheet of aluminum. Looks like maybe 1/16, 18 gauge, I believe. So we're gonna use this to mount it. So now I'm trying to envision how we're gonna mount it on a wall. So do I make this like one big part, or can maybe I can extrude down here, like tangent? So here, let me try to do this before anything. So let's open up this part. What if we did this? Okay, what if we did this? We look at this edge. Oh, this is gonna be weird. I need to just define a plane first. So let me do this. So we want it parallel. We want it coincident though. And then we want to flip the normal so we could see that way. And then we're going to place that plane. You'll see why I did that. I'll show you some more quick tips. So what we're going to do, we're going to sketch. We'll probably use a rectangle. Something like this. And then we want this to be tangent. And then we want this line to be horizontal with the origin. Or horizontal. So that way it's fully defined. We just need to find the length of this thing. We'll just say, I don't know, looks like 1.25 inches roughly. And then all we'll do is create this center line, so something like this, and then we'll mirror the entity. So we could also mirror sketches as well, so we don't have to waste time recreating things. So we could do something like that, right? So what I'm gonna do is extrude, and I'm gonna reverse the direction, and then make it up to surface. We'll say here, right? And we'll draw that down. Oh no, I wanted to go below. Okay, I made a mistake. Hold on. Let's see. Let's edit sketch. Sorry about that. Let me see. Okay, let's get rid of that relation. We don't want this to be horizontal. Want to get rid of this relation. We want this to be. Why is it doing that? Hold on. I think I messed up here as well. Where's I think I know why. Okay, I made the wrong geometric relation, which is this one. Let's delete all. Okay, let's change this so that this point is coincident with the outer circle, so that whenever I move this, it stays along the outside path. Hopefully I'm not going too fast. But so it's on the outside path. We want this line to be maybe collinear with this, like that. This is what I want. And then what we can do is let me exit sketch real quick. Let me go normal again. Yeah, basically something like that. And then we could attach the motors on this wall. I don't like this too much, simply because of this right here. This right here is a problem. You see how it's like a hard cut, hard edge, or a hard dip right here? That is a significant sign of failure when it's under load or stress. A way to combat that is to have a fillet or a radius that curves up, like nicely curves into it. So let me do this a little engineering. I don't want to go too deep into this yet, but stress concentration. Let me show you guys this. So if you, let me show you, can I get a bigger graph? Yeah, let's open this up. I know you guys probably don't want to see graphs and stuff, but essentially what we have here is kind of what we have in that scenario, this hard edge. You see this hard edge on this curve right here. See, that's hard. Like, I call it hard, but because it's like right angle. So if you remember that, the right angle is related to this radius, small r. So if you look at the radius, it's r over d, I realize. But essentially, the smaller the radius, the more likely it could crack or bend at that point. So if you want to decrease the possibility of that, you basically round it out. Make it a smooth transition. You don't want an abrupt transition. Abrupt transitions usually are failure modes. So if you want, so I see that and I want to avoid it completely, just in case, like, I don't know, maybe the robot will not break, but maybe I don't know, maybe vibration due to the motor. If we attach it this way, it might shake it enough where it'll damage or fracture right here. That may be a little too extreme. I don't think it'll do that, but you know, we want to avoid sharp edges. Even here is an issue. Like if you look at this edge, that's also an issue. But since the wall is relatively thick on this side, it's not as much of an issue. Relative to here, this is fairly thin, and I feel like if I were to like grab this bottom end and just pull it, it'll just rip right off. So there's that. Okay, so I'm gonna leave it here for now. I'm gonna save this assembly, and that's because it's already 8:30 my time, and I want to catch some sleep for tomorrow because I have work tomorrow. So hopefully you guys enjoyed this stream. We got pretty far today. We were pretty productive. If you want to watch the stream later, or if you didn't catch the beginning of the stream, if you wanted to see that, it was just me looking up parts for this project. But you can catch that on my YouTube channel. If you guys are watching on YouTube, it'll be live on my channel. There's a section on YouTube. All right, see you, Dane. I'll see you tomorrow, or if you're gonna be here tomorrow, I'll see you soon. But if you guys want to watch the live stream, or it'll be archived on my channel. We're already on part 4 or 5, and we've done a lot so far. We're starting to get into the actual building and designing of this thing, so it'll be pretty fun. If you want to catch more streams, I stream Monday, Tuesday, Wednesday, 6:30 p.m. to 8:30 p.m. PDT or Los Angeles time. So you guys could catch it then. All right, Dan, I'll see you here tomorrow then. So I'm just letting you guys know. You guys could watch it there, or you could watch it on Twitch as well if you guys are more accustomed to that. But Twitch doesn't archive the streams always. YouTube does. I believe it takes 30 days before Twitch removes archived streams. So there's that. So that's all I'm gonna say for tonight. I'll see you guys tomorrow. All right. If you guys have any ideas or any design and suggestions, feel free to let me know. I may look like the expert, but I'm not. I'm learning as much as, or I'm learning in this process as well. So feel free to leave any suggestions, and yeah. So I'll see you guys tomorrow.